Before we start, recall the definition that drives this whole video. A set P is called perfect if two things hold. First, P is closed. Second, every single point of P is a limit point of P. In other words, P has no isolated points. Zoom in on any point of P as close as you like, and you keep finding other points of P. A closed interval from A to B is the basic example. It is closed, and every point inside it, including the endpoints, is a limit point. But take a closed set with an isolated point, say the point 0, together with the interval from 1 to 2. Around 0, there is a small neighborhood containing no other point of the set. 0 is not a limit point, so this set is closed but not perfect. Here is the first main theorem. Let P be a non-empty perfect set in k-dimensional Euclidean space. Then, P is uncountable, not just infinite, uncountable. The mere requirement that every point be a limit point forces the set to be enormous. First, a quick observation. Since P is non-empty and every point of P is a limit point, P must have limit points, and a finite set has no limit points at all. So, P is at least infinite. The whole content of the theorem is upgrading infinite to uncountable, and we do that by contradiction. Suppose for contradiction that P were countable. Then we could list every point of P in a single sequence, x1, x2, x3, and so on. Every point of P appears somewhere on this list. Our goal is to build a point of P that the list misses, which is impossible, so the assumption must collapse. Here is the strategy. We will construct a shrinking sequence of neighborhoods, V1, V2, V3, and so on. Each one nested inside the previous, each one still meeting P, and each one deliberately dodging the next point on the list. Start anywhere. Let V1 be any neighborhood of x1. The open ball of all points whose distance to x1 is less than some radius r. Open ball, dashed boundary. It certainly meets P, since x1 itself lies in it. One piece of notation we will lean on. V1 bar, the closure of V1, is the closed ball, all points whose distance to x1 is at most r. Solid boundary. Closures will let us trap points later using compactness. Suppose Vn has been constructed and that Vn still contains at least one point of P. That is the inductive hypothesis. We must build Vn plus 1 with the same property while throwing the point xn out for good. Why is dodging possible? Because Vn meets P, and every point of P is a limit point of P. So inside Vn, there are points of P crowding arbitrarily close together. And we can place a small ball, Vn plus 1, satisfying three properties. 1. The closure of Vn plus 1 sits inside Vn. 2. Xn does not lie in the closure of Vn plus 1. 3. Vn plus 1 still meets P. Property. 3 is exactly the inductive hypothesis for the next step, so the construction runs forever. Now set Kn equal to Vn bar intersect P. Each Kn is an intersection of two closed sets, hence closed, and it lives inside a ball, hence bounded. Closed and bounded in Euclidean space. By Hina-Borel, every Kn is compact. Property 1 of the construction gives nesting. Each Kn plus 1 sits inside Kn. Property 3 gives life. Each Kn is non-empty because Vn contains a point of P, and that point also lies in the closure. And property 2 is the kicker. The point xn was expelled from the closure of Vn plus 1. So xn is not in Kn plus 1. Therefore, no point of the list survives in the intersection of all the Kn. But every point of P is on the list. Since each Kn is a subset of P, and no point of P lies in the intersection of the Kn must be completely empty. And here is the contradiction. We proved earlier in this series that a nested sequence of non-empty compact sets always has a common point. The intersection cannot be empty. Our only assumption was that P is countable, so that assumption is false. P is uncountable. An immediate corollary. If A is less than B, the closed interval from A to B is closed, and every one of its points is a limit point. So it is a non-empty perfect set. And by the theorem we just proved, it is uncountable. And since the real line contains the interval from A to B, the real line is uncountable too. we have recovered one of the most famous facts in mathematics as a corollary about perfect sets. Now for the star of today's video. Our examples of perfect sets so far, intervals, are fat. They contain whole segments. Here is a natural question. Does there exist a perfect set in the real line that contains no segment at all? No interval inside it, however tiny? The answer is yes, and the construction is one of the most famous in mathematics, the Cantor set. Start with E0, the closed interval from 0 to 1. Remove the open middle third, the segment from 1/3 to 2/3. What remains is E1, the union of two closed intervals from 0 to 1/3 and from 2/3 to 1. Now repeat. Remove the open middle third of each of those two intervals. What remains is E2. 4 closed intervals from 0 to 1/9, from 2/9 to 3/9, from 6/9 to 7/9, and from 8/9 to 1. And keep going forever. At every stage, remove the open middle third of every interval still standing. We get E3, E4, E5, and so on, without end. Now record two facts about this sequence. A, the sets are nested and decreasing. Removing more can only shrink the set. So E1 contains E2, or E2 contains a 3, and so on. B, at stage n, En is a union of 2 to the n closed intervals, and each of them has length 3 to the minus n. The count on the right doubles at every stage, while the pieces shrink by a factor of 3. Define P to be the intersection of all the En. A point belongs to P exactly when it survives every single round of deletion. This set P is called the Cantor set. P is compact. Each En is a finite union of closed intervals, hence closed, so the intersection P is closed, and P lives inside the interval from 0 to 1, so it is bounded. Closed and bounded, by Heine-Borel, P is compact, and P is nonempty. The En form a nested sequence of nonempty compact sets, so by our earlier theorem, their intersection contains a point. In fact, we can see survivors directly. The endpoint of any interval at any stage is never removed afterward. 0, 1, 1/3, 2/3, all of them live in P forever. We claim P contains no segment. Look at what we removed. Every deleted middle third has the explicit form. The open segment from 3k plus 1/3 to the m to 3k plus 2 over 3 to the m for integers k and m. By construction, none of these segments meets P. Now take any segment whatsoever, from alpha to beta. Choose the stage m so large that 3 to the minus m is smaller than beta minus alpha over 6. At that stage, the removed gaps are spaced so finely that the segment from alpha to beta must contain one of them entirely. But that gap contains no point of P, so the segment from alpha to beta is not contained in P. Since the segment was arbitrary, P contains no segment at all, exactly what we were hoping for. Now the final property. P is perfect. Take any point x in P and let S be any segment containing x, however small. We must find another point of P inside S. Since x survives every stage, at stage n, the point x lies in exactly one of the closed intervals of En. Call it In. Its length is 3 to the minus n, which shrinks to 0, so for n large enough, In fits entirely inside S. Now take an endpoint of In that is different from x. Call it x sub n. Endpoints are never removed, so x sub n belongs to P. And since In sits inside S, the point x sub n lies in S as well. Every segment around x contains another point of the Cantor set. That is exactly the statement that x is a limit point of P. The point x was arbitrary, so P has no isolated points. P is closed, and every point of P is a limit point of P. The Cantor set is perfect. Step back and look at what we have built. The Cantor set is perfect, so by the first act of this video, it is uncountable. It has as many points as the entire real line, and yet it contains no segment whatsoever. Even more striking, add up everything we removed. 1 segment of length 1/3, 2 of length 1/9, 4 of length 1/27, and so on. The sum is 2 to the n minus 1 over 3 to the n summed over all n, which equals exactly 1. We remove total length 1 from an interval of length 1. The Cantor set has total length 0, yet uncountably many points remain. The set is also self-similar. The part of P inside the interval from 0 to 1/3 is a perfect 1/3 scale copy of all of P, and the same on the right. Zoom in forever, and the structure never simplifies. Whenever you think a statement about subsets of the real line is obvious, test it against the Cantor set. It is the canonical counterexample of real analysis, and it will appear again and again in this series. Final act, connectedness. Two subsets, A and B of a metric space, are called separated if A intersect B bar is empty, and A bar intersect B is empty. In words, no point of A lies in the closure of B, and no point of B lies in the closure of A. The sets do not even touch each other's boundaries, and a set E is called connected if E is not a union of two non-empty separated sets. If you can split E into two non-empty pieces that do not touch, E is disconnected. If no such split exists, E is connected. It is genuinely one piece. A warning before the theorem. Separated is strictly stronger than disjoint. Take A, the closed interval from 0 to 1, and B, the open segment from 1 to 2. They are disjoint, no common point. But they are not separated. The point 1 belongs to A, and 1 is a limit point of B, so 1 lies in B bar. The intersection of A with the closure of B is not empty. By contrast, drop the endpoint. The open segments from 0 to 1 and from 1 to 2 are separated. Neither contains the point 1, and the closures only meet at 1, which belongs to neither set. Disjoint open intervals with a missing point between them, genuinely separated. Here is the second main theorem. A subset E of the real line is connected if, and only if, it has the following property. Whenever x and y belong to E, and z lies strictly between them, then z also belongs to E. Connected means no holes. On the real line, the connected sets are exactly the intervals, in the broadest sense of the word. First direction. Suppose the property fails. There exist x and y in E, and a point z strictly between them, with z not in E. We use the whole to cut E in two. Let A sub zo be the part of E to the left of z, and B sub zu the part of E to the right of z. Since zu itself is missing from E, these two pieces together make up all of E. Both pieces are non-empty. X lies in a sub z, and y lies in B sub z, and they are separated. The closure of A sub z stays at or to the left of z, while B sub z lies strictly to the right of z, and symmetrically the other way. So E is a union of two non-empty separated sets. E is not connected. That proves connected implies the betweenness property. Now the converse. Suppose E is not connected. E is a union of two non-empty separated sets, A and B. Pick a point X in A and a point Y in B. Without loss of generality, X is less than Y. Define Z to be the supremum of the set. A intersect the closed interval from X to Y, the rightmost frontier that A reaches inside this interval. We proved earlier in the series that the supremum of a bounded set lies in its closure, so Z lies in A bar. Since A and B are separated, A bar does not meet B, so Z is not in B. In particular, Z is not equal to Y, which gives X less than or equal to Z, and Zn strictly less than Y. Case 1. Z does not belong to A. Then Z belongs to neither A nor B, so Z is not in E, and Z is strictly between X and Y. We have found a hole. The betweenness property fails. Case 2. Z does belong to A. Then, by separation, Z is not in the closure of B, so some little interval around Z avoids B entirely, and we can pick a point. Z's one with Z, less than Z, one less than Y, and Z1 not in B. But Z1 is strictly bigger than the supremum Z, so Z1 cannot be in A either. Again, Z1 is in neither piece, so Z1 is not in E, and it lies strictly between X and Y. A hole again. In both cases, a disconnected E has a hole between two of its points. Together with the first direction, the equivalence is complete. A subset of the real line is connected exactly when it has no gaps. Perfect sets are uncountable. The Cantor set is uncountable, has length 0, and contains no segment. And the connected subsets of the real line are exactly the sets without gaps. Thanks for watching. If this kind of careful, step-by-step analysis is useful to you, consider liking the video and subscribing. See you in the next one.